Welcome, RustConf. Good afternoon, and thanks for coming to this session. We will be talking about C to Rust migrations. We will cover both the strategic level, so we'll look about the way you could go and approach such a project, as well as the tactical level, the challenges that you run into when you try to port specific C modules over to Rust, specifically when those modules use idioms that may not necessarily translate cleanly to Rust as a language. Before we get into the content, let's get introduced. As Ernest was saying, my name is Luca Palmieri, and I work as a principal engineering consultant for Maymatter, a consulting company based in Europe, which, among other things, specializes in Rust. I've been in the Rust community for 8 years, 7 professionally. I've written libraries, tools, articles, but I'm probably best known as being the author of Zero to Production in Rust, a book that teaches you backend development using Rust as the underlying technology. In the last 2 years, I also started a new project called Pavex. It's a new backend framework that you may want to try out. If either of the two things are interesting, links are on the slide. Enough with the chit-chat, let's get to the meat of things. Everything we will be talking about today happens in the context of a collaboration between Redis and Maymatter. Redis, as an organization, maintains the very popular key-value store, in-memory key-value store Redis, often used for caching and queuing. What fewer people do know is that over the years, Redis has grown a set of extension modules that layer additional higher-level functionality on top of the storage core. One of these extension modules is Redis Query Engine, and it's going to be the protagonist of our story today. Redis Query Engine allows you to define indexes over the key value data that you store inside Redis. And you can then use those indexes to perform pretty powerful queries. For example, here, using FT search, we're looking for all the identifiers of the item whose descriptions contain either Bluetooth or headphones, and whose price is in the 070 bracket. The kind of queries you might find yourself running on a SQL database or a NoSQL instance. Pretty powerful, pretty neat stuff. Redis Query Engine as a code base is structured as a dynamic library, so an extension module that you load into Redis. And it's currently written in C. It clocks more or less 63,000 lines of production C code, discounting tests, benchmarks, and auxiliary data artifacts. Now, Redis as an organization has decided that they want to migrate this over to Rust. Their main goal being ruling out memory safety bugs, thus increasing the trust and the stability of the product as a whole for customers. Redis is not new to migrations from C to Rust, as few people may know. They've done this before. In 2020, they rewrote another one of their extensions, Redis JSON, the one that gives JSON as a native first-class data type inside of Redis, from C to Rust. In that case, it was a from-scratch rewrite. So they started a new repo called Redis JSON 2, as it should, started to rewrite until they got feature parity with the existing feature set, and then swapped. So the next version of Redis JSON was actually the Rust code base. And the size at the moment of the swap, so at the moment this repo was archived, was 1,300 lines of Rust. So much smaller than Redis Query Engine, which is 63,000. But that's not the only obstacle of following the same strategy. The main reason why Redis Query Engine can't be rewritten from scratch using rewrite and then swap approach is that it is a moving target. There are multiple teams of full-time software engineers that are adding features, fixing bugs, and improving performance on a daily basis. So you'd be chasing a target that gets farther and farther into the future while trying to kind of bridge the gap, which is quite large. So it's a lot less risky, a lot more likely to succeed to rewrite in place incrementally. Now, what does that mean? You need to look at the C code base as a graph of modules. In this fictional C code base, in this fictional module graph, every single square is a C header file and its implementation. And every arrow is an import, so linking two modules together as a dependency. You look at this module graph, and you try to find the leaves, the modules that have no dependencies themselves. In this fictional graph, you can see at the bottom, AC and AD do not depend on any other module. So what you do, you rewrite one of those in Rust. The way this looks, you get the functionality implemented as a pure Rust module, and then you wrap that in a Rust FFI layer. So a layer of C-compatible types and C-compatible functions that allow the rest of the C code to consume the new Rust module, usually through a header file that's been auto-generated by something like cbind. You do this for AC, then you do this for AD. Now, AA, that used to depend on 2 C modules, now depends on 2 Rust modules, which means you can port it over to Rust 2. Rinse and repeat many, 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 many times, and eventually the whole graph is orange, and you've rewritten your code base to Rust. Unfortunately, real-world code bases do not quite have such neatly organized module dependency graphs. This is a snapshot of the Redis query engine module dependency graph took before the start of the project. You can see, you can spot that there are leaves, so there are places you can start that have no C dependencies. But as you get closer to the core of the code base, that gets harder and harder. There's going to be cycles, and it's not that easy to disentangle these modules. So the reality of doing such a port is much closer to this slide. So you will have your pure Rust module re-implementing the functionality of the target module that you're hoping to swap, but you will still defer a little bit to C code, calling into other modules that you can't quite port at the same time. And then as the project progresses, you will try to prune these C dependencies, thus increasing the island of safety, increasing the island of code where Rust is calling into Rust, and the borrow checker can verify that you're doing things correctly. Now, if you look at a project as at the boxes and arrows level, as a good old software architect would do, everything is easy. I color this orange, that is done, then I color this other thing orange, and eventually the whole project is complete. The reality of things is a lot messier and is a lot more complicated and requires much more creative thinking in trying to come up with solutions. So to give you a taste of that, we're going to look at the specifics of trying to port one module. TrieMap, a data structure, the very first module we ported in the C to Rust migration project. It will give us an opportunity to get a sense for the type of challenges that you may find in different shapes and forms in other types of C to Rust ports. Before we get started, let's try to understand what a TrieMap is. So a TrieMap is a map, first and foremost. So it's a way to associate values with keys. In these examples, the keys are strings, so cool, biker, beast, and bike. Those are going to be our keys. And the values are emojis. You can think of a TrieMap as a hash map whose keys are vectors of bytes, or sequences, more generally. And the payload can be whatever. It can be a number, can be strings, can be pointers. In most cases, in this project, it's going to be pointers. You would go about using a TrieMap whenever you're looking for very specific properties. In particular, you're looking for optimized prefix searches. So being able to very quickly find all the keys inside your data set that start with a given prefix, like car. And so you go car, card, cargo, et cetera, et cetera. And secondly, you may want to use this when the keys you're storing do share prefixes with each other. Then a TrieMap will be able to store them compactly, significantly reducing the amount of memory used at runtime by the data structure. How does that work? Let's go through an example to get the sense of things. So we're going to try to build a TrieMap instance from scratch, storing the 4 key value pairs on the left. As you can see on the right, little spoiler, it's a tree-based data structure. So it's going to be nodes and edges carefully arranged in such a way to get the properties I just described. We start from a single key value pair, a bike and the bike emoji. Very simple. 1 key value pair, 1 node. The node is going to have a label set to bike and a payload set to the bike emoji. Things get more interesting when we try to store biker. Now, bike is a prefix of biker. So rather than storing biker in full as a node label, we're just going to store the difference. We're going to add a child node to the bike root, and that node is going to have R at its label, as well as the biker emoji as its payload. So biker doesn't exist exactly as it is in the tree, but you can recover it as the concatenation of the 2 nodes that lead to the payload associated with the biker key. We could then try to store bis. Now, bis is not a prefix of bike, nor is bike a prefix of bis. It's difficult to say. But they do share a common prefix, which is bi. So what can we do? We can take the tree as it exists now and split the bike node. So we're going to split it into a bi root, which is going to have no payload, because bi is not a key in our current TrieMap. And then we're going to get ke as a child node. So just like biker, now bike is recovered as the concatenation of 2 nodes labels. Once the tree is in this shape, then storing bis becomes simple. We do exactly the same thing we did when storing biker. So we store the suffix. We have a child node that's going to have s as the label, and as the payload is going to have the victory emoji. Last but not least, you have cool. Cool doesn't share a prefix with any of the keys which are currently in the trie. So we do the same thing we did for this, but this time the root is going to have an empty label. So this is the little trick when you have no prefixes to share. And then you make cool a direct child of the root. That's how you go about building a TrieMap, and you can kind of see or grasp why it does key compression, because it is structured in such a way to try to fully leverage the little bits that are shared among the different keys. And then prefix searches work in the same way. If you think about what a node needs to keep track of logically, there's 3 pieces of information. A node needs to have a label, which is going to be a sequence of bytes. It needs to know if it has a payload or not, so that's going to be an option. And it has 1 or 0 or more children, so that's going to be a vector of pointers. It is interesting to see our node is modeled in the C code that we're trying to port. I'll give you a few seconds to look at that while I grab some water. OK, the water is very difficult to drink, so we'll resume immediately. It is a very interesting definition. So you have a bunch of normal fields, right? So you have label length, number of children, flags, data payload. So far, so good, very boring. The interesting stuff are the ghost fields. Like, what do these comments actually mean? They're saying, here are the first letters of the child, and now comes the children pointers. But there's no actual field. You need to go and look at the rest of the code to kind of piece together what this looks like in memory. And I've spent a lot of hours coming up with this graph to try to make this simple to understand. There's 3 key properties of a TrieMap node in the C implementation. Number 1, it is a single heap allocation. All the fields inside the node live in a contiguous slab of memory, which is wonderful for things like cache friendliness. You don't have to jump around, chase pointers. Everything lives nicely located next to each other. Number 2, some of the fields have an offset and a length that's only known at compile time. The fields in green, in particular, they depend on runtime parameters. Like the label is going to be as long as the actual label that you're going to store. And the length of the label, you will only find out at runtime for a specific module. The same applies to the number of children. Those arrays will be longer or shorter, depending on how many children that specific node has. So you can't kind of allocate this heap region for a given set, for a given size. You need to figure it out for specific instances. And third, last but not least, the layout is packed. That's what Pragma Pack 1 was doing in the definition, which means that we have no padding whatsoever between fields, which in turn implies that some fields are going to be misaligned. So for example, if you look at the children array in this specific example, children array contains pointers to the children, so each pointer is going to be 8 aligned. But children 0, the first of the pointers, starts at offset 20, which is not quite a multiple of 8. Knocked off a bunch of things. Beautiful. Now, interesting questions for you in the audience. Do you think you can replicate this in Rust using only safe Rust? Oh, wow. Someone mustered the courage to say, no, you can't. If you think the answer is yes, you go grab me after the talk, and then you explain me how you do it. That invalidates the next 20 minutes. Anyway, you need to do it with unsafe Rust. Like, as far as I know, it is impossible to do it in safe Rust. And the TrieMap C module, it's kind of big. Like, it is 1,000 lines of C code. That's because the TrieMap does support a variety of specialized iterators to do traversals in certain ways. Plus, it is heavily optimized when you need to do splits and merges and a bunch of other operations. And so we were wondering, what do we do? Like, do we try to rewrite this in Rust straight? We go straight for the kill. We emulate this one-to-one using the same memory layout. At the same time, we implement all the methods. Or do we do something else? We were a bit scared, so we decided to do it in 2 steps. First step, we decided to establish a baseline. In this context, a baseline is a functionally equivalent reimplementation, which means that it behaves the same, and it has exactly the same public API. So it is indistinguishable from a consumer perspective, looking at the shape of the functions that are exposed. But its internals are intentionally simplified. We make no attempt, only minor attempts really, to get this to be fast. What we are focused on is to get it to be correct. In the Rust version of our baseline, this is what the node definition looks like. You will recognize more or less the same fields of the C version. So you have the data, the label, the children pointers. We're also tracking the first byte of the children label as a way not to have to chase too many pointers. We're doing some optimizations. So the VECs are low memory versions. They use U16s rather than U sizes to track capacity and length. But other than that, we're making no attempt to squeeze out the last ounce of performance. And most importantly, this implementation, this baseline TrieMap, is 100% safe Rust. So we don't have to worry about the correctness of the unsafe code when we're reasoning about the correctness of the data structure. Why would you do this? Number one, you want to deepen your understanding of the original implementation. I don't know about you folks. I don't implement TrieMaps on the regular. I also don't use TrieMaps on the regular. So you got to wrap your head around how the data structure is supposed to behave. And you need to try to reduce the cognitive load when you then go for the optimization steps. So separating those things in 2 stages makes it so that if you have then to do a second implementation that's going to be more optimized, you won't have to worry about too much about how this thing is supposed to work. But the other benefits are very tangible. Number 2, you want an exhaustive test suite. The original C code did have tests for 80-something% test coverage. We ported those over to Rust, and then we added a bunch more to get the coverage over to 96%, I think. We added property-based testing, just as many checks as we could possibly add to make sure that we fully specify the behavior of this module. And the nice thing about the baseline is that it has the same public API of whatever final version we are going to ship, which means that if we choose to do a second, more optimized implementation, we get to reuse the test suite. We don't have to change anything. It's going to be exactly the same. And the same rationale goes for micro benchmarks. If you want to establish if something is fast enough, you need to have a way to quantify it. Redis Query Engine, as a project, does have a pretty comprehensive suite of end-to-end benchmarks. So you spin up a database instance, you fire off a bunch of queries, you measure throughput, you measure latency, you measure memory usage. And this is very useful, but it's also a very slow feedback loop. It takes like an hour and a half to do this for all the different cases. And it's difficult, depending on what you're working on, to see how the small piece contributes to the bigger picture. So it is a lot more useful to have micro benchmarks which are tied directly to the operations you're trying to perform. That makes the feedback loop run in seconds, tens of seconds at most. And so you can really see why certain patterns work and why they don't. So we did all these things. We got the coverage to 95%, as I was mentioning, and then we benchmarked our baseline. Not a surprise, it isn't fast enough. You can see in this violin plot from Criterion 3 different implementations. The first one is the C implementation. So we're trying to find a certain key inside the map. That's the fastest, which runs in 20 nanoseconds, more or less. In the middle, you have a Rust baseline, which is roughly twice as slow. And in the bottom line, you will see one of the crates from Crates.io, Radix 3, which is a off-the-shelf implementation of a TrieMap. So we wanted that as a reference to know how well we were doing, because a question was also, do we need to write our own TrieMap? Can we find one? Well, apparently not. And the same relative picture in terms of speed-ups or slowdowns, depending on how you look at it, holds consistently across the different operations that were benchmarked. So we did conclude, in fact, as we kind of suspected, that the baseline was too slow to be viable from a production perspective, and also too memory hungry. It uses more or less twice as much memory as the original version. And that's because if you have pointers and containers, you are tracking their capacity. You're tracking their length. You have the pointers themselves. All of those things are overhead that if you sum it together, kind of amounts to a fair amount of memory in this kind of data structure. Which leads us to the second attempt, which I ironically named Let the Unsafe Flow, because we're going to have a lot of that. Let's refresh our memory. This is the C memory layout. So single heap allocation, variable length fields, packed. We decided we still didn't want to go for the kill, so we still didn't want to go for exactly the same layout. We're going to make one last simplifying assumption. We're going to try not to pack fields together. And this is for 2 reasons. Number 1, dealing with misaligned reads and writes is painful. Getting them right is non-trivial. So if we can remove a bunch of complexity, we should be doing it. Second, if you do things aligned, there's a high likelihood that's going to be faster. So we might need to evaluate if the speed up is enough to justify whatever increase in memory usage this new layout is going to give us. So this is the final version of our Rust node layout. They are the same fields as the C version. We just swap them in terms of order in such a way to create a single padding region. So you have 1 aligned and 2 aligned fields to the left, and then you have 8 aligned fields to the right. We are assuming, as you can see in this diagram, that data, the payload, even though that is generic, we're optimizing for the case where it is 8 aligned. Because we do know in practice, inside the database is always a pointer. So it makes sense to optimize for the 8 aligned case. This creates a single padding region, which you can see there in gray stripes. Worst case scenario, those are 7 bytes of padding. Best case scenario, those are 0 bytes of padding. That depends on the length of the label and the number of children. So on average, 3 to 4 bytes of padding. And the assumption is that in most nodes, that's not going to matter. Because either the label is going to be much longer, or the number of children is going to be much higher. So the padding overhead is going to be negligible. Beautiful. What's the challenge with this? Node data is a dynamically sized type using Rust lingo, or DST, if you like acronyms, which means that we don't know its size and compile time. It depends on some parameters that we only know at runtime. If you've been doing Rust for a while, you know DSTs. You've been using DSTs. Slices are DSTs. Trade objects are DSTs. The challenge here is that we need to define a custom DST. It's not about using one. It's about making one viable. Morally, if Rust was more powerful in my fantasy Rust syntax, this is what a node definition would look like. So we would have a couple of normal fields, so the label length and the number of children, and then we would have 3 arrays whose length is the value of one of the first fields. This is the type of data structure that we're working with. Unfortunately, Rust isn't quite as powerful, and probably will never be, to express something like this. So we need to go for something a lot more implicit. We're going to have a stack type called node data that's going to have a pointer to the heap allocation. And then we're going to have a phantom data there just to inform the type system that we are actually generic over a type parameter. And then on the heap size, we can't represent the full layout of the heap allocation, but we can represent the part that's known at compile time that we're going to call the node header. That's going to be the label length and the number of children. For those 2 fields, we know the offset, and we know the size statically. So we can write them as a type. And so if you go back to the layout, those correspond to the 2 fields in blue. That's why we're using those as the header. How do you go about creating an instance of this kind of data structure? That's when it gets tricky. Well, you got to think here about the algorithm that the compiler itself follows every time you're trying to allocate something on the heap, where you're trying to do a box new, whatever type you have. You need to compute the layout, so you need to know how big the allocation needs to be and what the alignment of that memory needs to be. Then you actually allocate it using the allocator. And then you need to initialize the fields at the correct offsets within that heap allocation. If you're doing this for a size type, the compiler is going to do all of this for you. So it's going to compute the layout at compile time, so it's going to know it statically. Box new is going to know what the layout is, so it's just going to allocate the right memory with the right size and alignment. And the compiler is going to just copy the fields to the right locations. Very easy. All the heavy lifting is hidden. But here, we're doing things by hand, so we need to do this ourselves. We start by going at alloc. This is the signature of the alloc function in the standard library. It expects a layout as input. Layout, as we anticipated, it's the size and the alignment of the memory you need. Since our type can be expressed as an actual struct, we need to compute this layout at runtime. And layout, the Rust type, has a lot of useful utility methods to do this kind of computation. So you can go to layout and say, give me the layout for this field. So you can give it the layout for a node header, for an array on a given length. And then you can call extend to kind of combine them together as if you were defining a C representation compatible type which has those fields. So this allows us to actually compute the layout of the fantasy type that I've shown you before. You then take this layout, you pass it to alloc. That gives you back a row pointer. That row pointer may be null if the allocation failed. If it didn't fail, congrats. You now have a bunch of memory on the heap. But that's not enough. Like, that memory is garbage. It's uninitialized memory. You can't work with it. You need to initialize all the fields, which boils down to a lot of pointer operations. So you have the first field, the node header. You're going to pointer right, the node header. Then you have the label. You got to offset to the right offset where the label is supposed to be, and then copy the label over from a slice or some other location where the label lives. Rinse and repeat for every single field. And if this looks innocent enough, although tedious, when you're creating a new node instance, it actually gets rather tricky while you're doing splitting and merges. Because there, rather than alloc, you're using realloc. And then it's about moving data in very careful ways. So we do need unsafe, because we're doing a lot of pointer manipulations. And we do need more than a pinch of unsafe. The final version has 128 unsafe blocks, as well as 21 unsafe private methods to kind of make the situation a bit more manageable. Which leads us nicely into the last section, which is how do you go about managing this much unsafe code? The North Star, the thing that you're striving for in these cases, It's to keep the unsafe contained. So you want to have no unsafe whatsoever in the public API. That reduces dramatically the scope of the analysis when you need to determine if your code has or does not have any kind of undefined behavior. Because remember, the whole reason we're porting over to Rust is that we want no memory safety bugs. So it is important that we treat unsafe extremely seriously. In the case of TrieMap, this is relatively easy. So TrieMap exposes an API that is pretty much like the one you find in HashMap. Insertions, removals, retrievals. It's very easy to make this safe. So that is easily checked. Nonetheless, inside, there's a lot of radioactive material. So how do you go about it? Number one, tools and patterns. Tools. You want to run Miri as a CI check. Miri is a Rust tool that is optionally shipped as part of the tool chain. And you can use it to detect undefined behavior. What you would normally do, you would run your tests under Miri, which means running them in a carefully crafted environment. And Miri will compare the runtime of your test against a couple of different memory models, which are currently competing to become Rust memory model. And if it detects any violation, it's going to report it to you. So if you run it as a CI check and things pass under the tree-borrow memory model, you're more or less good. Unfortunately, Miri is good at telling you that something is wrong, not necessarily at explaining you very clearly what is wrong and why. So what I do actually recommend you do is you want to abuse the bug assertions. So some of the safety preconditions in some unsafe methods can be checked at runtime. You don't want to check them because they may introduce overhead in your production builds. But in debug builds, if you require a pointer to be correctly aligned, you can check that it's correctly aligned. This will make it so that your tests will fail with more meaningful error messages or easier to debug error messages, that's speeding up the iteration loop. Going back to tools, everyone here probably knows Clippy. Clippy has a bunch of optional lints. I do recommend enabling 2 of those when you're working on projects that have a lot of unsafe. Number 1, you want to force 1 unsafe block per unsafe operation. And number 2, you want to enforce that every single unsafe block is documented. This makes it so that you have safety comments for every single unsafe expression. So you can't just bundle them together and have like a global safety comment, which goes nicely with the fairly strict guidelines that we follow when it comes to safety documentation. This comes from an article from Jack Wren called The 3 Basic Rules of Safety Hygiene, which I recommend everyone to go and check out. It's a beautiful article. But when you're working with unsafe, there's 2 kinds of safety documentation. On one side, you have unsafe functions. When you have an unsafe function definition, you need to document the safety preconditions that must be verified so that you can call this safely. When you have an unsafe function invocation, so an unsafe expression, you must document why the preconditions are met. So you have 2 pieces of documentation that need to talk to each other. It's a lot easier to do this correctly if they're structured, ideally as a numbered list. So you can then go check side by side that all the preconditions have been met and they are correctly specified. Now, there's no tooling to do this, unfortunately, and even the standard library only uses bulleted lists, which is not ideal, but you can still strive to do this as correctly as possible. So for example, copying and overlapping, as in the safety section, 4 different preconditions. When you invoke copying and overlapping, this is a snapshot from the specific TrieMap implementation, you can put it side to side with the stu docs and make sure that every single precondition is accounted for and that the explanations do make sense. Nonetheless, these safety comments are pretty lengthy, right? So I said 128 blocks. This is about 10 lines. There's 1,000 lines of safety comments, so it's a bit much. So what you want to do is you want to create APIs that make it less verbose to do these kinds of operations, which I call defend in depth. So design unsafe private APIs, because we're not exposing that to the public API, that are very hard to misuse. What that means is that you want to build a hierarchy of abstractions. You start from the lowest layer. So if we look at the heap allocation that we've been discussing about the node in the TrieMap, we need to keep track of a bunch of metadata about that allocation. That's the layout and then the offset of every single feed within that allocation. But to use pointer metadata with a pointer, you first need to prove that the 2 things are compatible, so that the allocation behind that specific pointer uses a layout that is compatible with the layout that's inside that pointer metadata instance, which means that every time you're doing that operations, this requires a lot of safety comments. So what you can do is you can build a higher level abstraction when you pair the 2 together. So you have a pointer with metadata, very original name. And you put the pointer and the metadata inside of that. Now, you will still need to prove that these two things go well together, but you will only have to do it once when you construct such an instance. Usually, at the point in time where you're doing that, it's pretty obvious that that's the case. So that makes it also simpler to explain what is safe. After that, this instance gives you invariants, the one that you can see up there, 1, 2, 3. And you can refer to those invariants when you're doing those pointer operations inside the implementation of the methods. So for example, this exposes a copy from slice non-overlapping as a way to initialize the children first bytes array. You can see that underneath, it's still doing the copy non-overlapping from the standard library. But thanks to the invariants that we do have inside this data structure, we're able to discard some of those preconditions without exposing them to the higher level consumer. So the higher level consumer, instead of 4 or 5, gets only 3 safety preconditions, and they're fairly easy to reason about. Basically, the sugars too, you have exclusive access to this buffer, like morally immutable reference. And this is actually non-overlapping, as the name of the method implies. And you're not writing more elements than the capacity of the buffer. Like, these things are easy to reason about. They are the domain logic of the thing you're trying to do, rather than being somewhat esoteric things about memory being contiguous and coming from the global allocator. And that's all for the safety section. Now, if I have a few seconds, I'll just go with some parting thoughts. Let's recap what we did. So we had a C module, a C TrieMap implementation, 1,000 lines, 80-something% coverage, and no micro benchmarks. We rewrote that as Rust. It is more verbose, so it's almost 2,000 lines. But we have reduced by an order of magnitude the amount of code that needs to be inspected to determine if there is or there isn't any kind of memory safety bugs. So we've gone from 1,000 lines of potentially unsafe code down to 100 lines of unsafe code. We also boosted the test coverage up to 95.6%, and now we have a micro-benchmark suite that, while it served a purpose during the port, so it allowed us to establish that indeed the Rust version was fast enough to replace the C version, it becomes an artifact that lives in the future. So if you were to make any changes today to the Rust version, you can use the same micro-benchmarks to assess that they don't regress or how much do they improve the performance of the implementation. Which brings me to a rather meta point. Then when you're trying to do a C to Rust migration, or generally a port of any kind, it is not just about changing programming language. It's very often about paying off tech debt and just reevaluating assumptions. So the Rust version doesn't use a packed layout, which simplifies the code considerably. We don't have to deal with unaligned memory accesses. That was something that we were able to do because we were able to challenge the assumptions of the original code. We had time to spend reevaluating if the things in the original implementation still made sense today. So it's very often about making the code that used to be there more maintainable for the future, rather than just moving that over to Rust. But last but not least, and that's the thing that gives me the most satisfaction, when I say we do an incremental rewrite, it's because we want to ship, and we shipped. So if you're using the latest version of Redis, 8.2, which came out in August, you're using our Rust TrieMap. So if you're running Redis query engine, you're now running a Rust code, which is something I'm very proud to say. And that's the note I wanted to end it up today. Thank you very much for staying until the end of the session. If we have time for questions, I'll take questions on stage. Otherwise, you can grab me outside, and I'm happy to chat for as long as you like.
Yeah, we can take 2 questions.
Nice.
Hey, thanks for the talk. Really interesting. I'm curious if you looked at the zero copy crate to help with some of the DST stuff. Because
absolutely, yes, I have. So zero copy is able to do a custom DST as long as it has a single unsized field, which is the last one. So if we had a single slice as the only thing that was variable length, and that was the last field in the struct definition, then we would be able to use zero copy. In this case, as you have seen, it's not the last field. There's multiples, and they depend on different fields. So the macros from zero copy are not powerful enough. Cool. It also, it comes from being from different domains. Zero copy is optimized for, I think, network parsing, where you have those kind of formats more often, like header and then variable length body.
Cool, thanks.
But if that worked, I would be able to use it. Let's put it this way.
Hi there. I was just hoping you could describe maybe something, or is it similar to the problem set being sort of solved by something like the Aho-Krazik crate, which is providing like a tri-tree sort of searching tool? I'm just wondering if that's something that's similar, and what would be the sort of difference in performance characteristics to go with something like the TrieMap?
I'm not familiar with the crate you're talking about, so I think I can't answer
Okay,
the
maybe
question.
we'll ask after. Thank you.
Yes.
All right, thank you very much. Please give Luca another massive hand.
Thank you.